The first category is what the book is calling primary identities. I'm calling these definitions. And they're all familiar to you. They're things like tangent theta equals sine theta over cosine theta. By now you should know these like the back of your hand. You can see those on the first line. The second category is the odd-even identities. As an example, the sine of minus theta equals minus the sine of theta, because sine is an odd function. And I guess I should be clear, the cosine of minus theta is just equal to the cosine of theta, because theta is an even function. And you should be familiar with this, as well as the odd or evenness of the other basic trig functions, tangent, cotangent, secant, cosecant. We finished on Monday talking about the, I guess I should write here, odd, even. We finished on Monday talking about the co-function identities. Co in this case you can think of as complementary, right? Relationships between the angles that would be the smaller angles of a right triangle. For example, the sine of 90 degrees minus theta is equal to the cosine of theta. And you can switch the theta and the 90 minus theta. It works the same either way. And similarly, there are, because of this relationship, you can, if you took 1 over each of these, you'd find that 1 over the cosecant of 90 minus theta is 1 over the secant of theta. Again, these are the co-function identities. So that's as far as we got. We didn't really get to go over this worksheet, and that's fine, because we're gonna try and do as many examples today as possible. I'll let you guys have a chance to play with some of them. But before I do, I want to introduce one more family of identities. I kind of feel like they're the most important because this is a definition. This is very simple. It's not quite trivial. Again, this is also very simple, not quite trivial. This next family is a little broader in scope, and it just comes up over and over and over in mathematics. Some of you may be familiar with it already. It's generally these are referred to as Pythagorean identities, and you'll see why almost immediately. Before you see why, I'm just going to state why. Because they are equivalent to the Pythagorean theorem. You can use the Pythagorean theorem to prove these, and starting with the Pythagorean identity, you can prove the Pythagorean theorem. So let's see how that works. Question? No, it's throat clear. Okay. It's a fine line, Okay. So what we're going to do is we're going to look at a right triangle. one of its smaller angles is theta. We're going to call the hypotenuse r. We'll call this leg y and this leg x. Pretty straightforward. So we're going to first write down a description of the sine of theta. If this seems really simple, it is really simple. You just have to follow it through. Sine of theta is what? That's going to be y over r. Or as we're going to use it here, y equals r sine of theta. That should be familiar to you from both polar coordinates and somewhere else. All right. Cosine of theta is equal to x over r, or x equals r cosine theta. So now what we want to do is we want to write the Pythagorean theorem as it relates to this. The Pythagorean theorem says x squared plus y squared equals r squared. And now is the final, pretty much the final important step. I'm going to substitute in here for x and y into this equation. All right, let's try that. Here we have r squared cosine squared theta. Y is r sine theta, so r squared sine squared theta, and that's equal to r squared. But of course, we can divide by r squared, and we just have, I'm going to write it a little, I'm going to rearrange it. Sine squared plus theta plus cosine squared theta equals 1. Who here was familiar with this beforehand? Anyone? A few of you. Okay, you've seen it. All right. This is the primary way we think of the Pythagorean identity. It's really useful, and let me write that up here. Sine squared theta plus cosine squared theta equals 1. Now, I said there was a family of identities. I'm going to show you something related in a minute, but I also, before we go there, it's good to be familiar with this in a few different forms, because it comes up a lot, and it has a lot of useful purposes. So the first two forms I want to point out are very simple. If I subtract sine squared from both sides, I'm going to get cosine squared equals 1 minus sine squared. That's one useful form. And symmetrically, sine squared equals 1 minus cosine squared. But we can take these one step further. We can solve for cosine or sine here. I hope I'm not confusing anyone by not writing theta each time. Just taking a little time here. I can say cosine of theta equals the square root of 1 minus sine squared. Actually, we introduced an extra solution here. It's actually plus or minus depending. And likewise, sine is equal to plus or minus square root of 1 minus cosine. Now, the reason I gave you these two forms is because sometimes you won't see this, but you will see one of these. And you go, aha, 1 minus sine squared, I can simplify that. 1 minus cosine squared, I can simplify that. The reason these are really useful is sometimes you have an expression with sines and cosines. how did we get there? Well, you had tangents and cotangents, and you followed my advice from Monday, and you converted everything to sines and cosines. But now you have a sine and a cosine, and you want to get rid of one. Well, this turns a cosine into a sine, or a sine into a cosine. So, given an expression with trig functions, we can almost always, get it down to where there's just one function in there. And that's going to help us in some problems.
Can you go back? Can you pull the board out?
I'll give you a minute. Okay. So, I just want to leave this here. I won't stretch anyone's eyesight if I come up over and use this board, will I? So there's a couple other members of this family that you can get very easily. Right? Let me show you how you do that. If I have sine squared plus cosine squared equals 1, and if I divide by sine squared, well, this is 1. Cosine squared over sine squared. Cosine over sine squared. Cosine over sine is cotangent. And what is 1 over sine squared? That's 1 over the sine squared. Cosecant squared. Okay. Now, you might not recognize that right away as a Pythagorean identity, but it's part of the family, right? Okay, again, starting with sine squared plus cosine squared equals 1. This time, I'm going to divide by cosine squared. Cosine squared. So now, sine over cosine squared, that's tangent squared, plus 1 equals secant squared. Okay, so here we have our happy family of Pythagorean identities. So maybe I should make a list of strategies here. I've given you one, which was convert to sines and cosines. Second, and maybe even more important, is look for a Pythagorean identity, and I'm going to throw in the word substitution. See if there's some place that the Pythagorean identity is going to help you solve this problem. Okay, let that sit for a second. I want to do a couple examples just to give you a feel for how this works. So we can put this up here. All right. So the first problem I want to show you is I want you to simplify the following. Simplify. 1 minus cosine squared theta times cotangent squared theta. See what we can do with this. So following my advice, the first thing I'm going to do is make sure everything's a sine or a cosine. Cotangent is cosine over sine, so squared is cosine squared over sine squared. All right. Now I want to look for a Pythagorean identity. Does anyone see the Pythagorean identity I can substitute here?
Yeah, sine the square.
1 minus cosine.
Ah, 1 minus cosine. That's just sine squared. And clearly here I've got sine squared over sine squared. That's just usually 1. So the simplification is this becomes cosine squared theta. Okay, that was just a simplified problem. Let's try something that requests a little more of you. Questions about that? That seems straightforward, pretty simple, yeah. That's what this identity stuff, once you kind of get comfortable with it, they're fun, they're little puzzles, you know, you have to kind of work your way through. I was going to say fun, but I might offend some of you. Very idea, math could be fun. All right. Okay, this problem says, solve this equation. Cosine squared theta plus cosine squared theta tangent squared theta equals 2.6 cosine theta. Wow, that looks pretty intimidating, doesn't it? All right, let's don't panic. Let's first convert everything to sines and cosines. Tangent squared, that's sine squared theta over cosine squared theta equals 2.6 cosine theta. Okay, looks good. Cosine squared cancels, okay. All right, now what? Look at number 2 again. Look for a Pythagorean identity.
Cosine squared plus sine squared is 1.
Ah! Oh, that really helps. Okay, now all I have to do, cosine equals 1 over 2.6, and that, of course, brings us back to our calculator. So, I don't really want to pull the screens down and run this. I'm just going to inverse cosine of 1 divided by 2.6. I get 67.38 degrees. So if I plug 67.38 into this original equation, I expect it to work. All right. One of the next thing we're going to be doing is which is basically the same type of stuff, but we're going to be a little more formal. We're going to verify identities. Now, I think I mentioned on Monday that verifying an identity is a little like a proof. In fact, that's exactly what it is.